All right, this is going to be the first video for lessons for the differential equations course. This will be for section 1.1, which is on just kind of introduction to what differential equations are and some terminology and ways to classify differential equations that we're going to need going forward. All right, so what is a differential equation? So a differential equation is just an equation. So it's an expression that contains an equal side which states that the two sides are equal, as opposed to an expression which doesn't contain an equation. So it's an equation, but where at least one of the terms in either side of the equation contains a derivative. That's really all it is, an equation that contains a derivative, okay? So here's a couple of examples of differential equations, right? We've got dy dx plus 5y equals e to the x equation, there's a derivative in a term. This one has a second derivative as well as a first derivative as well as the function. Okay, so a solution to a differential equation is itself an equation. So this is a little different, right? When we have algebra equations like x plus 3y equals 6, and maybe you want to plug in a value for x, let's say, and solve for y, right? Or maybe we want to say, what's the solution of this equation? It's a set of xy points, right? So the solution for an algebraic function or an algebra equation is our values, right? Solution would be values, okay? That's different because you plug values into the different places in the equation and show that the equation is true. In this case, because there's derivatives, we have to have the solution be itself in a complete equation because I have to be able to take the derivative of that equation to plug in for the derivative parts and then the entire equation. So for example, in this equation, if you wanted to verify if a particular equation was true where you had y equals some function of x, let's say, then you could take the derivative of that function and plug it in here, and then plug the original f of x in here and verify that this left side equaled the right side. So the big difference between differential equations and regular equations is that the solution is not values of the variables, it's an equation. The solution is itself an equation. Okay, so one thing we might be asked is to verify that a particular function or a particular equation is a solution to a given differential equation. So if we're given this differential equation, dy dt equals 5e to the 0.05t, we want to verify that this equation is a solution. Then, okay, the first thing I'm going to have to do is the only place I see the y is in this derivative. So I'm going to have to take the derivative of this. So dy dt, well, let's see. That would be, we have a constant here. Here's a t, so this is the derivative is a copy times the derivative of the inside, which is 0.05. And then because this is a constant here, the derivative is 0, right? So this would be 0.05 times 100, so that's 5 e to the 0.05t. So the idea is that I should be able to substitute this in place of this in this equation. And so if I do that, I get 5 e to the 0.05t equals 5 e to the 0.05t. And sure enough, that equation, when you take its derivative and plug it in, check, this is a solution. Okay, so that's how we find out whether or not something is a solution to a differential equation. We just take whatever derivatives are required and then plug that in to the original equation to the differential equation to see whether or not it does make the differential equation true. All right. So there's a lot of different symbols for derivatives, and we need to be aware of all of them. The most common ones are these first two that we're going to encounter in the course. The first is called Leibniz notation, and so that's the dy dt or d squared dy dt squared for second derivative, or d squared z dx squared with partial symbols if we're talking about a partial derivative, right? And then for prime, we also have prime notation, which if we have y as a dependent variable and some variable like x or t is the independent variable, then the first derivative can be written y prime, second derivative y double prime, third derivative y triple prime, and then above that we go y, and then in parentheses we put a 4 for fourth derivative and so on. Right? We also, for partial derivatives, have a subscript notation that the partial, so the equivalent of partial derivative of, say, some function f with respect to y can be written as f sub y, right? And this one would be first take the partial derivative of f with respect to x, and then take the result of that and take the partial derivative with respect to y. right? So there's a partial derivative notations here. And then in physics, sometimes people will encounter what's called Newton's dot notation. So it's the same as prime notation except with dots, and usually just three, because it typically in physics goes up to, position, velocity, and acceleration. So three dots. Okay, we're mostly going to stick with these, and we're not going to really see partial derivatives because this course is a course in ordinary differential equations, which will not include partial derivatives for most of the parts, things that we're going to talk about. Okay, so some terminology. We're going to be talking about learning mainly different methods of solving a given differential equation. So we'll be given a differential equation, and then we'll learn various ways that we can use to find a solution or solutions to that differential equation, the equations which are solutions. And at a couple places in the course, we'll stop and we'll investigate applications of differential equations in the real world, as well as just learning the procedures for finding the solutions. Okay, there's a lot of different techniques that exist for finding the solutions to differential equations. It's actually fairly challenging to try to come up with them on your own, but most of the course, what we're going to learn is if a differential equation has a particular form, then people have already figured out that a particular format for a solution is the format that will work in that case. So it's going to be kind of, I call it like a recipe class. Like if it looks like this, then you use this procedure to find the solution. And on the other hand, if it looks like this, then you use a different procedure, something like that. Okay. And the different techniques are based upon the different formats of differential equations. So we often classify differential equations into different types and groups. And throughout the course, we'll be learning different techniques that to apply to different things. Okay. So the rest of 1.1, most of it here has to do with classifications. So the first thing is we might classify a differential equation by what we call its type, okay? The two primary types are ordinary differential equations and partial differential equations. So to qualify as an ordinary differential equation, abbreviated ODE, all the derivatives have to be ordinary derivatives, no partial derivatives, okay? So if you had things like this, like dy dx plus 5y equals e to the x, or this has a second order derivative, but it's still a regular derivative. In other words, that means that in this case, y is some function of only x, right? Regular function. Same thing here, y is some function of x. Now, we're dealing with the first derivative and the second derivative, but this is still an ordinary function, not a multivariable function, right? You can actually even have, although we won't see it too much in this course, you can have more than one dependent variable, but you can still only have one independent variable. So you might have x is some function of t, and y is some different function also of t, right? So I have two dependent variables, but they both depend on this same independent variable t, right? So if they both depend on t, then that means that they're still ordinary derivatives, right? dx dt is an ordinary derivative, dy dt is an ordinary derivative, and therefore this would be an ordinary differential equation, right? But if you have equations like this, like where you have, let's say that u seems to be the dependent variable, but it's dependent on both x and y. So u is a function not only of x, but of x and y, which would make it a multivariable function, which would require calculus 3. Then the derivatives are called partial derivatives, and that the resulting equation is a partial differential equation. Those are even more challenging to solve. And as a result, we will not be doing any of that in this course. This introduction differential equations course focuses only on ordinary differential equations. There's enough going on even with that. Okay. Okay, the second thing we classify a differential equation by is by its order, and an order is just the highest derivative that appears in the equation. So if you have something that has a first derivative, no, just a function without the variable, but then there's a second order derivative here, then the highest order derivative in here is a second order derivative. So we call this a second order differential equation, and often I'll abbreviate differential equation DE. Okay, in this case, I have a second derivative, a first derivative, and a third derivative. So this would be a third order differential equation because the highest is a third order derivative. In this case, we have a second derivative here. This is a first derivative, but then the result of that is being cubed. So this is still a first derivative here. And that means that this is still a second order differential equation because this is the highest term as far as the highest type of derivative that we're doing. This is still a first derivative, just the result is being cubed. Okay, so we might need to classify by order. And then the next part we're going to talk about is classifying by linearity, but that depends on what is the dependent and independent variables. So it will not be true throughout the course that y will always be a function of x. It can be any mix of different letters. So you have to carefully consider, well, what is dependent upon what? So in this equation, um, I see a y prime here. So there's a derivative that has a y. That tells me that the dependent variable is y. In other words, y is some function of the other variable here, which appears to be x, right? So the independent variable would be x, and y is the dependent variable because it depends on x. And the clue about which is the prime here. Y prime means that the y is the dependent variable. Here we have a second derivative of y in terms of x. That's telling me that y is the dependent variable and the independent variable is x. Same thing here. I've got a derivative. It's a third order derivative, dx dy. That means x is dependent upon y. So in this equation, the dependent variable is y and the independent variable is, I'm sorry, the dependent variable is x and the independent variable is y. So these are reversed. So this is how you tell what variable is dependent on the other. Look for the derivatives and see which one is being primed. That's always the dependent variable, or if it's in fraction form like Leibniz notation, then the numerator is always the dependent variable and the independent variable is in the denominator. In this case, I have only one term here with a derivative, x prime. That means x is the dependent variable and the y is the independent variable. Okay, that's important because of the next type of classification that we're going to do for differential equations, which is classification by linearity. Okay, so for an nth order or ordinary differential equation where y is dependent and x is independent, the the um, the the differential equation is called linear if it can be written in this form. So you can think of this as crazy looking, but whichever the dependent variable is, we can have the variable itself, we can have the first derivative, the second derivative, the third derivative, the fourth derivative, and any number of derivatives, okay, in the terms there, right? But for this to be considered linear, all of those things I just underlined have to be linear. In other words, we can't have any squares or square roots or 1/overs or anything like that. So you can't have y cubed, you can't have 1 over y, right? You can't be taking the derivative y dy dx and then squaring it or something like that. So linear terms for the variables of the dependent variable. And then the coefficients of each of those terms, as well as the function that doesn't contain any dependent variable on the right-hand side, all of those things can either be constants or they can be functions. They can depend on the independent variables. So in this case, they could be functions of x, but they can't contain any y's anywhere. Okay. All right, so that's the way I remember it, is that if you identify the dependent variable, then you can list it in this order from left to right, the highest order derivative down to just the variable itself, and then a constant or all the terms that have no y in them. Okay, and then all of those pieces have to be linear, and then all of the coefficients can be functions of only the x but not the y. Okay, so let's take a look at a few examples. These are all examples of linear differential equations. So we have dy dx here. That means y is the dependent variable, x is the independent variable. So if you list it out here, we've got the y term and we've got the dy dx. Neither of those are square. That's good. And then as far as coefficients, we have constant, constant, constant. So this is all good. Okay, if we look at this term here, same thing. It looks like dy dx, y is the dependent variable, right? And all of the coefficients are either constants or they're functions, but they're functions only of the x, right? So there's no y in this function. So this is still considered a linear differential equation. Okay, here we've got, again, dependency y prime. So y is the dependent variable. So we have a y prime term, a y double prime term, y prime, y. All of those are linear. There's no squares. And then the coefficients are 2, -3, 1, and 5. All of those are either constants or functions of x. That's fine. Okay. Let's look at this. We've got, let's see, dy. So y is a dependent variable. So we've got a third derivative, a first derivative, and a y. And if you look at the coefficients, right, 1, x, -5, e to the x. All of those are contain no y's. They're either constants or they're only functions of x. And this one here, what I would do is take this term, because I have x prime here, that means x is the dependent variable, and I'd move it to the other side so it's in this form. And then that means we have just one term over here that has the dependent variable x prime. And that means that it's linear, but it's the coefficient. This coefficient is now only in terms of the dependent variable y, or sorry, independent variable y, and this over here is also only contains no x's, right? So you can't have the dependent variable. Okay, now here's some examples of things that are not linear, nonlinear. If we went through that same kind of thing here, here's the y prime and y, so the dependent variable is y. But if we look at the coefficients, right, this is okay because e to the x contains only x's, the 2 is fine, but this is bad because this contains the dependent variable. We're not allowed to have a coefficient that contains the dependent variable. It makes this nonlinear. Okay, here we have the, let's see, a y in terms of x, so there's a second derivative. And then actually this whole thing, uh, it's a function of y, right? But it doesn't really contain a y. So this is sort of like, yeah, like a function of y. It's not just y itself. So really it should be on this side. We should write this as d squared y dx squared equals e to the y minus sine y, right? And so we've got the term here with the y. This coefficient over here is 1, so that's fine, but on the other side, this can only be a function of x. So the fact that it contains y's makes this one not okay, not linear. Okay, here we've got, let's see, dx in terms of y. So now the dependent variable is x. We have a third order derivative, a non-derivative, and then a function over here, right? Then we have to look. So the problem with this one is that, when you have this y here, that can't be to the squared or cubed or 1 over y. The problem is the fact that that x is being cubed. That makes this nonlinear. This part over here is actually okay because this is now in terms of the independent variable. And then this last one, we have, let's see, the only derivative here is x prime. That makes x the dependent variable. And so if you were to, well, you can see the problem here. Its coefficient contains x's. It's okay for that to be a function of y, but not x. Okay, so a bunch of different classifications. This will become more important later when we learn the various techniques, because some techniques will apply only when differential equations are linear, and then you have to use other techniques for nonlinear differential equations. Okay, so throughout the course, we're going to learn different ways to obtain these solutions. But in this first section, we might just be asked to verify that a solution provided is indeed a solution. So like we saw on the first screen, we'll just take the derivative of the solution, plug it in as necessary to verify that the given differential equation is equal on both sides. So a couple things to know about that. The first is that if the solution turns out to be just y equals 0, it's just 0, then that solution is often called, that should be En, then the solution is often called a trivial solution because it doesn't give us any meaningful information about the problem scenario. It is true that, like, if we had, dy dx equals ky, and you wanted to say y equals 0, I mean, that's true that the derivative of 0 is 0 and it's equal to 0, but that doesn't really tell me anything. So that type of a solution is considered trivial. It's not, it is a solution, but it doesn't really give us meaningful information. Okay. Another issue is if the solution or the original differential equation has some kind of restricted domain, like a fraction where there are some values in the domain that would cause us to divide by 0, for example, right? Then the solution itself is only defined over what we call an interval of definition, where it exists. It has existence and validity. Okay, so that's going to be a list of the domain values that are allowed in both the original differential equation as well as in the solution. So basically, if anything, either in the solution or in the original differential equation would cause something to be undefined, then the solution is not defined for that portion of the domain. Okay, and then one last thing, but because the solution to a differential equation is an equation itself, it can be graphed, and the graph of that solution is referred to as a solution curve. We're going to see more of that in later sections. All right, so this first section was all just about terminology, and you should have enough to be able to do the 1.1 homework at this point.